Hello, honors chemistry students. Today we will be covering Unit 10, Part D, the fourth and final section of Unit 10, involving volume mass relationships of gases and the stoichiometry of gases. Normally, we would go into great depth on gas stoichiometry. We will not be doing that this year due to a lack of time. We will be skimming the surface of gas stoichiometry. For those of you who take AP Chem next year, you will go in much more depth on gas stoichiometry. We start with a new law. So we have quite a few gas laws in this unit. And we've already had Gay-Lussac's law. Now we have another one of Gay-Lussac's law, his law of combining volumes of gases. And I think it's pretty simple to understand. At constant temperature and pressure, coefficients in balanced equations represent ratios of volumes of gaseous reactants too. So, in other words, in situations of involving STP, remember, STP is standard temperature and pressure. The standard temperature of science is 273 Kelvin, or 0 degrees Celsius, and the standard pressure is 1 atmosphere. So at those constant temperatures and pressures, coefficients in a chemical equation represent a ratio of volumes. So let's look at this a little bit. Key to this, every reactant and product must be a gas in order to use this law on a balanced chemical equation. So here's a very simple chemical equation. 2 hydrogen gas particles plus 1 oxygen gas particle gives us 2 water gas particles. And we know with coefficients that the coefficients can mean several things. Like I just said, they can mean particles or molecules. They can mean moles, so 2 moles of hydrogen and 1 mole of oxygen and 2 moles of water. And now, according to Gay-Lussac's law, this now means that there are 2 liters, when 2 liters of hydrogen reacts with 1 liter of oxygen, that gives us 2 liters of water, which we can see here. So 2 liters of hydrogen chemically reacted with 1 liter of oxygen gives us 2 liters of water. That's Gay-Lussac's law. And that leads into the stoichiometry of gases involving chemical equations. So remember that equation coefficients give you mole ratios. So I just talked about that. They can give you molecule ratios. And now if everything in the chemical reaction is a gas, it can give you volume ratios. Moles and molecules does not matter what the conditions are. Volume, it does. You can only use Gay-Lussac's law when everything is at the same temperature and pressure, which oftentimes will be STP. So, very simple equation. I got 3 oxygen molecules that react to produce 2 ozone molecules, or 2 O3s. So I have some stoichiometry done already. In here, we're using the chart method instead of the big table method to do these. Next year, when you take AP Chem, you'll use the table method like we did earlier this year in our stoichiometry unit. So here's a question. How many liters of ozone can be made from 12 liters of oxygen? You can only do this conversion if everything is a gas, and in this case, the oxygen is a gas, and the ozone, O3, is a gas. So you start with what you have, are given in the problem, 12 liters of oxygen. And then I want liters of oxygen to cancel, and the coefficient in front of oxygen is 3. I want to have liters of ozone left over, so the coefficient in front of ozone is 2. So just like we've done all year long, you go 12 times 2, divided by 3, and we get a final answer of 8.0 liters of ozone. Remember, coefficients can also be used as moles. So we've done these types of problems all year long. How many moles of oxygen are needed to make 24 moles of ozone? So I start with what I know, 24 moles of ozone. I want ozone to cancel out, so the coefficient is 2. I want moles of oxygen left over, so the coefficient is 3. That's 24 times 3 divided by 2 to give us 36 moles of oxygen. And then finally, how many molecules? The last thing we can use a coefficient for. How many molecules of ozone can be made from 18 molecules of oxygen? So what I know, 18 molecules of oxygen. I want molecules of oxygen to cancel out, so there's a 3 there. I want ozone left over, 2 molecules of ozone, so 18 times 2 divided by 3 gives me a final answer of 12 molecules of ozone. That's very simple gas stoichiometry at the top problem, and the other two are just very simple stoichiometry problems from what we had earlier in this semester. That leads into the molar volume of gases. So this is like molar mass. Remember, molar mass is calculated from the periodic table, and our unit is always in grams per mole, so G/mol. So it's very similar to that, but we are not using the periodic table in this case. We are using the volume of 1 mole of that substance. And the ideal gas law can always give us this answer. 1 mole of any gas has the same volume as any other gas on Earth at the same temperature and pressure. So at STP, 1 mole of every gas on Earth has the exact same volume. It doesn't matter if it's oxygen, hydrogen, ozone, water, nitrogen dioxide, carbon dioxide. 1 mole of any of those gases at STP, they all have the same volume, and that's the molar volume of gases. So let me do the example to prove it, to prove that this could be any gas on Earth at STP has the same volume. So the pressure of STP is 1 atmosphere. 1 mole is in. The temperature of STP is 0 degrees Celsius or 273 Kelvin. I plug those all in to my PV equals nRT, and I solve for V, and I get V equals 22.4 liters. And that, my friends, is the molar volume of gases. All gases on Earth at STP have a volume of 22.4 liters, which we would say the molar volume of gases is 22.4 liters per mole, L/mol. So that just restates everything I just said. The volume of 1 mole of gas at 1 atmosphere and 0 degrees Celsius is 22.4 liters. 22.4 liters of any gas has 1 mole of particles, but that gas will have a different mass. Even though all gases have the same volume, 22.4, the mass of that gas will be different, and we can solve that using stoichiometry. Standard temperature and pressure, we've talked about already, 1 atmosphere of pressure and 273 Kelvin temperature. Now, just to prove that gases have different masses, these are all 1 mole of gas. And using the periodic table, we can say, just using hydrogen as an example, hydrogen is 2.02 grams of hydrogen, but its volume is 22.4. Chlorine gas has a mass of 71.0 grams, but its volume is 22.4. Every gas on here is 22.4 liters, but they all have a different mass because they have different molar masses on the periodic table. So, to do two stoichiometry problems using this, we're going to have to go back and forth between this molar volume of gases and the molar mass of that gas. A chemical reaction produces that many moles of oxygen. What volume in liters is occupied by this gas sample at STP? And remember, 1 mole of any gas is 22.4 liters at STP. So starting with what I know, 0.0680 moles. And I want to convert moles into a volume. So I use my molar volume. I want moles to cancel. 22.4 liters in 1 mole. I take 0.0680 times 22.4, and I get a final answer of 1.52 liters of oxygen gas. Example 2 is a little bit more difficult. A chemical reaction produced 98 milliliters of sulfur dioxide at STP. What was the mass of that gas? So I have to figure out where I start and where I want to finish. So these bullet points kind of tell us that I have to start with milliliters, but I have to finish with a mass. And that this is really one of the longest stoichiometry problems we've done, in terms of you have 3 different calculations you have to make to get to your final answer. So I have to convert milliliters to liters first, because 22.4 liters, I have to use liters. Then once I find that, I have to convert liters to moles using that 22.4, and then once I find that, I have to use my periodic table to convert moles to grams. So start with what I know, 98.0 milliliters. I want milliliters to cancel. There are 1,000 milliliters in a liter. Then I can use my molar volume to get liters to cancel, moles left over, and then I go to the periodic table. Sulfur dioxide has a molar mass of 64.07, so that's 1 sulfur plus 2 oxygens. And I go 98 divided by 1,000 divided by 22.4 times 64.07, and I get a final answer of 0.280 grams of sulfur dioxide. Example 3. I have a chemical reaction that produces 3.1 grams of CO2. What volume will it have? So this is kind of going backwards from the previous problem. I have to convert grams of a gas into volume of a gas. And I want that volume to be in milliliters. STP lets me know that I can use the number 22.4. So the first thing I have to do is use the periodic table to change it to moles. And then I can use my molar volume, 22.4, to change it to liters, and then I can convert from liters to milliliters. So 3.1 grams of CO2, molar mass of CO2 is 44.01 from the periodic table. So 3.1 divided by 44.01. Then I want liters, so I use my molar volume. I multiply by 22.4, and that gives me a liter answer. And then I have to convert that to milliliters by multiplying by 1,000 to get a final answer of 1,600 milliliters of CO2. Just a very simple problem here in example 4. How many moles of gas are in a container with a volume of 2.46 liters at STP? So all I need here is my molar volume, 22.4, and I get liters to cancel and moles left over, so 2.46 divided by 22.4 gives me a final answer of 0.110 moles of this gas. All right, those 4 example problems should very much help you do the 10D assignment. Highly recommend. If you're listening right now, you've watched the video, and that's good. Good luck on those 10D problems, and I will talk to you all later.